So this is a force on a wire. And we already have this formula, right, that the force is I, L, B, sine theta, right? And so if we've got a particle moving in a magnetic field, so let's just have a positive particle, and let's have it moving this way in some magnetic field. And since it's so much easier to draw a magnetic field out of the page, I'm going to draw it like that, okay? Then we've got some charge moving, right? Okay? And since current is Q, right, over T, right? If I substitute Q over T in for that, and we say that the thing moves some distance L in that time T, okay? Then it's really not very hard to derive what the formula is. All we have to do is take the T so the substitution here is that the current is charge divided by time. We know this, yes? Coulombs per second, okay? And then all we have to do is just take the T and go like this. I think we can do this because it's like, yeah? Okay, and then of course the rate at which it moves, distance divided by time, is just velocity, isn't it? Yeah? Okay, so we end up with this force is Q times V times B sine theta. Okay. Remember, though, that now it gets more interesting because the charge can be plus or minus, right? So if it's a negative charge, the force will be negative the direction we predict with our right-hand rule. And if it's a positive charge, it'll be positive that direction, yeah? So that makes it a little more exciting. Yeah, there we have it. Okay, so it's the velocity here crossed into this is our index finger now, and then this is our magnetic field, is our middle finger, right? Okay, so in the case of this guy right here, the force is actually going to be which way? Well, index finger that way, magnetic field out of the page. Which way is the force? Force is going to be down, right? Okay, and in general, the force is always going to be at right angles to the velocity, right? This is the force, here's the velocity, and if the thing is moving down the page, if it then curves around so that it's going down the page, now the force will be which way? To the left, and when it's going that way, it'll be up, and when it's going up the page, it'll be to the right. In general, it'll always be towards some center, and so this thing is actually going to go in a circle. Almost all of these problems, let's see if I can do this. That's not too bad, right? In general, it's just going to go in a circle. If it's a uniform magnetic field, this thing is going to go turn itself in a circle, right?
So this what allows like electrons to go around the
Yeah, well, that's not a magnetic field, though. That's just orbit. That's just orbit, right? But it's a similar thing. It's not a magnetic force. It's just an electrostatic force.
But
yeah.
Like it's not going to go in a current, right? It's going to certainly get smaller.
It's gonna lose velocity. Yeah, it's actually gonna radiate energy, and so it will actually circle in. We're not going to consider that, right? But as it loses energy, it would slow down, and then the circle will get smaller and smaller. Yeah. Okay. So for these problems, let's hit the right arrow and just see where this takes us. See what it does. Right? So here's an example: a proton, right? It's moving in Earth's magnetic field, and it's 5 times 10 to the minus 5th Teslas. And let's suppose that this proton is moving exactly perpendicular to the magnetic field like that, right? The force then is going to be QVB sine theta, right? So it equals, well, positive 1.602 times 10 to the minus 19th coulombs, right? Times what's its velocity? 40 wow, this is a very accurate velocity, 4787.1 meters per second. Okay, right?
That scale, whatever they use.
Oh, 0.81, yeah, there we go. I know, isn't that amazing? I hope they know all those numbers for sure, right? Because if they didn't, it might be a disaster, right? And then this is 5.0 times 10 to the minus fifth Teslas, right? And then presumably the angle is 90 degrees, right? Can we stop? Can we not make little whiteboards and talk about them? Yeah, thank you. Okay, and then presumably the angle is 90 degrees, and so the sine of 90 is 1, and I'm not going to put that in there. And so let's calculate this. 1.602 e minus 19 times 4787.81 times 5e minus 5. And we get that the force is not very much force. Okay, that's not very much force, except it's one heck of a lot of force. Okay, I'm trying not to cuss so much. It's one heck of a lot of force for a proton, because protons have a mass of about 1.673 times 10 to the minus 27. So it's really going to accelerate quite a lot. But it's going fast, so we'll see. Okay, so that's our first question. Is there it is, and we've got the forces and everything, right? Okay. Yay, go team. Okay, but then the next question is, I believe, what's it going to do? Well, the force on that thing is actually going to be centripetal. Okay, so as if this is the proton and it's moving in the field like this, right? What you tend to do with these problems is you say, okay, QVB, this magnetic force, right, equals MA, right? Okay, and then what's our centripetal acceleration? Centripetal acceleration is, don't all speak at once. It's v squared over r. There you go. Okay. So for A, I'm going to say m times v squared over r, or it could be, by the way, m times 4 pi squared r over t squared. Right. But this is the one I want to do right now, because I want to get at the radius of curvature, and we have the velocity that this thing is going, right? And so now I can just set this thing up, and I guess what we want to solve for is, what is the radius that this thing is going to go around, right? This thing is going to go in a circle. What's the radius of that circle? That's what we're trying to figure out, right? Okay. So QVB sine theta. I'm not even going to use this. I'm just going to stuff this stuff in here. QVB equals mv squared over r. So how do we solve that for r? I think we could do this, can we? And then can I put the QB down there and the R up here? Yeah, kind of switch them around, right? Just switch it around. Okay, so R is going to be MV over QB. Yeah? Which is kind of cool, isn't it? Right? So this is the momentum. This is charge times magnetic field. So R is going to be 1.673 times 10 to the minus 27th kilograms, right? Its velocity is 4787.81 divided by charge, which is 1.602. And then the magnetic field is 5. Right? Somehow all these units must end up being meters, yeah? Yeah? So 1.673 E minus 27 times 4787.81. It'd be kind of weird if this came out like to some even number. Divided by 1.602 E minus 19. Divided by 5E minus 5. Oh my God. Almost. It's like 1 R equals 1.0000000.